Hey, this is John Buck. I'm going to talk today about binary hypothesis test. That is how we use a measurement to decide between two possible choices using the ideas of statistical signal processing. I always think this is actually the first real engineering application of the probability material we have in the class. The first sort of these decision rules are the first thing that we can do that's an engineering meaningful task based on the foundation we've built with conditional probabilities and densities. This is again part of my ongoing YouTube marathon making up for our snow day. This video assumes you've already seen the video on conditional density and hopefully the example of how to apply conditional densities because we're going to use those ideas. I'll make another video to follow this one with an example applying the idea or showing how we use the binary hypothesis test in a classic communication problem. Wrong page. All right, here we go. So for the binary hypothesis test, wrong color. All right, here we go. Binary hypothesis test. This time for sure, Rocky. What this is, when we talk about a binary hypothesis test, our goal here is to design a decision rule to choose between two alternatives based on measured data. And again, binary means two, so this is a case you can extend it to more. And also, we'll see as the class goes on, the data doesn't have to just be a scalar. It could be a vector or even a time signal. We'll see by the end of the class. But today we're going to focus on the case where the data is a scalar. For the two hypotheses, the way we offer the classic notation is that we have one of them we call the null hypothesis, which is sort of the normal, not interesting case. And then we have H1 is often called the alternate hypothesis. And these are generic names because the same picture, the same framework applies to so many different problems. And I'll talk in a minute about a bunch of examples to give you some practical ideas to make that more real to you. But it helps that we use these same ideas in engineering, in statistics, even in medical statistics, people use them, or medical diagnostics. We can talk about them also. But just to sort of give you a block diagram, again, the big picture idea is that we're going to have some data we measure X. That when we design a binary hypothesis, the idea of the binary hypothesis is ultimately going to tell us how to make a decision rule, g of x, where g is a function for each value of x that just takes one of two values. It's basically this choice or this guess, best guess, between saying, based on the data, do I think H naught happened? So I'm putting the little hat on H naught to say, this is my guess as opposed to the truth if I write it without it. And I'm going to come up and say, well, if I see some set of values of x, those are the times where I think it's best. I'll call that set D naught. So any x in that set, I think my best guess is H0. Otherwise, I think my best guess is H1. That's some region D1, which has to be the complement of D0. Every value of x has to get assigned to either guess H0 or guess H1. Okay, but to do that well, you say, well, I can't just do that. I need some more information. I need to know, if I'm going to make that guess, I need to know something about how the data depends on what's the true hypothesis. Is it H0 or H1? So every binary hypothesis test, when you design it, at a minimum has to know what's often called the signal model. And that is, how does the data depend on the true hypothesis? If the data is continuous, this will be a density. If the data is discrete, it will be a distribution or a PMF often. At a minimum, we have to have f of x h0, the conditional for the null hypothesis. Ideally, we like to have the alternate hypothesis too. But again, these two things together are often what we call the signal model. So at a minimum, we need those. We need to know something about how this data, which is a random variable, capital X, right? So maybe we could say that the data we're observing is some outcome on a random variable, capital X, and these tell us how the distribution of that data depends on which of the two hypotheses are true, and based on that, we're going to decide how to assign things. Ideally, in the best case, we also have what are known as the priors, which is to say we know the relative probabilities of H0 and H1. And we often abbreviate these as P sub 0, capital P sub 0 and capital P sub 1. And again, the technical name often for these is, these are the prior probabilities. So prior to making the data measurement, prior to getting the data, if we just had to guess blind, what's the probability that H0 is true versus H1? When we have these, it's a good thing, but sometimes we don't have these. There are situations where we don't know if this for true, and we have to take a different approach. If we have all four of these things, I'll show you in a bit, we can actually design a data rule that will minimize our probability of error, make as few bad decisions as possible, given all this data. But sometimes in real life we don't have these. Sometimes, even if we're really unlucky, we may not have the signal model. We may just have the noise model. But hopefully we usually have at least these two. Next class on Tuesday, we'll see a bit more about how the binary hypothesis test, how we handle the binary hypothesis test when we do not have the prior probabilities. Okay, so that's enough sort of general stuff. Let's talk about some examples, and then I'll give you a little more vocabulary. So if we go, we need a new page here. Again, I recognize that it's all been in sort of very general, abstract terms so far. So let's talk about examples of binary hypothesis tests. Some of these are classic engineering, some of these are a little more general, but they're all real life applications. Sort of the most common one is a communications problem, right? Where H0 is that binary and digital communications, that the sender transmitted 0, H1 means that they transmitted 1. So we get some measured voltage or pressure, and we're trying to decide which of the two bits were sent. Another very common one is in medical diagnostics. In this case, H0 will be the patient is healthy, like we've done a blood test or an X-ray or something, and we say based on that, the true thing is the patient healthy, or the patient is infected or injured or whatever, so we'll just say not healthy. And we're trying to use some data we've measured, which might be an X-ray, it might be an ultrasound, it might be a blood test, it could be any number of things, and we're trying to make an accurate guess of the patient's real health based on this noisy measurement of these things. It could be a blood pressure, many different things depending on what you're looking for. Another very classic engineering one is radar, that I'm going to look out based on the signal that's I transmit a pulse, and based on the signal coming back to me for each range, I'm trying to decide, looking up into the sky, there we say that H0 is there's no plane. That's sort of the default normal condition, even around an airport, right? And then we want to detect when there is a plane. Things that are maybe a little more non-classical, but still good examples, and particularly topical for the fact I'm recording this because we had a snow day, is to look at the data. Could be that some weather map, or some looking at a weather radar, and we try to say, the null case is the school will stay open. I'm trying to guess, looking the day ahead, when I'm trying to decide if I really need to finish my homework or not. I'm going to guess between, is the school going to stay open, or the alternate is the school will close based on how severe the forecast looks and all the weather data, right? So there's another topical thing, and one that was in the news, kind of a neat application. This was in the news a lot last year. So big scientific breakthrough with gravity waves. Right? It was a very great result, proving Einstein's relativity, that people were able to detect clearly for the first time gravity waves. So these people have had a long-going, very complicated physical instrument to do binary hypothesis tests where H0, for each moment in time, they're looking at the signals coming out of their interferometer, their optical instrument, and the typical situation is there's no gravity wave, but they really want to make sure if there is one that they see it. So H1 would say, hey, I just saw a gravity wave based on the measured data. Coming back to the framework, in most of these cases we can get conditional probabilities for both, though depending on medical diagnostics we may not have enough good data to say, well, what's the probability of having a certain blood pressure if you have this disease? People may or may not have enough data for that, but we certainly have it for the healthy case. In communications, we have usually, because we built the system, we have very good models. And in almost any good communication system, we have prior probabilities of zeros and ones, which if I have a good data compression system should be equal. Radar is often a case where I have very good conditional probabilities, but depending on the situation, I may or may not have good models of priors, and so that informs some of the things we'll see next time. And again, snow days we may not have very good priors either, but we sort of try to accumulate our best over our lifetime. Gravity waves, we again, the physicists they thought were very good models for how the signal would look different when a gravity wave was present, depending on the source of the gravity wave, what size black hole, or what other thing, the collapse of two black holes caused it. But they had no idea what the priors were. They didn't really know how to weight those, so it led to a different kind of test also. Okay, so that's just trying to make these abstract things real. A little more vocabulary we need when we talk about these things. We have, because it's such a classic problem and appears in so many ways, we have some other terminology people use for different events that we're going to look at. So maybe one way to the best way to show this maybe is to make a little box, and we say if on the top we have the decision. Let's actually make this pretty big so we can fill in a lot. On this side we have the truth. So the true situation is either H0 or H1. And then we have two possible decisions. We can guess H0 or H1. So if the truth is H0 and we guess H0, that's correct, right? That's a happy thing. And it's generally true that this is also correct. Depending on this context, it may be a happy thing or not. If it's a snow day, we're definitely happy. If it's a medical test telling us we have a disease, we might not be that happy, but it's still better than missing it, right? It's better than the alternative of someone being sick and the test saying they're not. So there's sort of two cases. The diagonal cases are the good ones. There are two cases here. This is if the truth is H0 and we guess H1. In engineering, we often call this a false alarm. Right? It's like we think there's a fire, we're guessing there's a fire, but there isn't. Technical statistics language, this is often called a type 1 error. The other, so this corner is one of the ways we can make an error, and the other one is when the truth is that the alternate hypothesis is true, but what we've made a incorrect guess that it is the null hypothesis. And this is, in engineering, this is often called a missed detection. And the statistical literature, medical literature, often calls this a type 2 error. And particularly in the medical context, these can have very different things. It can be bad to tell somebody they're sick when they're not, but it can be very bad to tell somebody they're healthy when in fact they have a serious disease. So in general, then we can put all these together. A couple other common pieces of vocabulary for that. In the classic statistical literature, then they say alpha is going to be the probability of that you guess H1 and actually H0 is true. So when you make the wrong choice that way, and beta in the classic statistical literature, engineers don't always use these terms, are for the other type of errors. And then overall, then the probability of error would be alpha plus beta, right? How likely I am to have H0 be true and guess H1 and these are disjoint, are mutually exclusive events, so I can add their probabilities. And this covers all the ways an error can happen, right? It has to be one of these two off the diagonal to have this, right? So sort of hidden in that, there are. I've sort of gotten ahead of it, but the event of having an error, or sometimes we might call that just the event E, is that I have H0 is true and I guess H1, or H1 is true and I guess H0. Right? That I have this sort of partition of the event that there's an error can be partitioned into these two disjoint alternatives, and therefore I can add their probabilities. Right? And so this would be, more technically, we say, well, why did I say H1? Well, that's because the value of X I saw was something that was in the region where I guess H1, and similarly, this would happen, because that's not equal, but what that's telling me, that implies that G of X was H0. So even though the data was really distributed according to what the conditional probability for H1, I got something for X. And I should mention earlier, these decision rules, the most common form is just an inequality. It says if X is below this value, guess H0. If it's above this value, we say H1 hat. Okay, and so as I mentioned earlier, there's sort of three main cases. The best case is when we have both models and both priors. And when we do that, we can come up with a decision rule that will minimize the probability of making an error. And that's what I'm going to show you next today. Two other common cases, the Neyman Pearson case happens when I don't have the prior probabilities. And so I'll show you an example next time in class. In that case, we make our choice based on a given false alarm rate. We do have a good model for the null hypothesis case, and we say there's a certain amount of false alarms we can tolerate, and we're going to base it on that, and then we'll see what our probability of detection is. The third case, that's the least helpful case, but does happen sometimes in scientific and medical research. When we're looking for something new, we don't know enough about what we're looking for, the new case of H1, to even say what its conditional density is. We have good data for f of x given H0, and so again, we'll make a decision rule that says what we want to tolerate some probability of error, which is often called the significance test. All right, so now those are sort of the three cases. Again, for the rest of the video today, I'm going to show you how we minimize the probability of error. So this would be, and this is building up to something we're going to call the likelihood ratio test that actually shows up in several of these different scenarios for hypotheses test. So again, we're going to assume we have both priors, P0 and P1, and that we have also both conditional densities. So f of x given H0, f of x given H1. Okay, and again, our goal now, we actually have enough information. So our goal in this case is to design our decision rule G of x to minimize the probability of an error, which we'll write P of E, like that. Right? Again, we saw a minute ago that what that happens, right? The event error is a union of two disjoint events. One is that H0 is true, and we get a value of x that's in the decision region D1, right? This is this place where we're going to say we've made a bad choice. We guessed H1. Or H1 was really true, but the value of x we got fell in the decision region D0. So if we're going to do this, another way we can use the continuous law of alternatives to say, well, the probability of an error. No, I'm going to just start that on the next page. Let's take that off. Oops, too far. So this is equivalent to, again, before I erased it. All right. So we're going to say the probability of an error, we can say, is actually, we can use the conditional thing. We could say it's the probability of getting the error given a particular value of the measurement, times the density, overall density of that measurement, and we're going to integrate that over all possible values of x, right? So basically we've conditioned on the measurement. We say for each measurement we see, what's the probability of getting an error? And this starts to connect with the things that we saw in the foundational video, right? Here's an example of an event conditioned on a continuous random variable that we had to define well. So if we're going to do this, we know we can break this into two terms, right, to get that value. And so it says for each value of x, we basically, if we want, each value of x doesn't depend on any others. So for each x, we want to choose what to minimize the probability of error. So for each value of little x, we want to design the decision rule. Or design is a big word. Just have the decision rule choose the more likely value. So if we choose the more likely value, we're going to minimize the probability of E, right? So we're going to, for each x, say, well, what's the probability? What that means is we're going to compare two things. We're going to say I'm going to look at the probability of H1 given that my measurement is x. And if that is bigger than the probability that H0 was true, given that x equals x. The way we write this is I put H1 hat up here. So it says this is my decision rule. If this side is bigger, I say H1. If it goes the other way, I say H0. And now we use the definition we had a little while ago, conditional probability of an event on a continuous random variable. Right? We can say this right-hand side here we saw was the probability would be the probability of H1 times the ratio of the conditional density over the overall density. So again, we have this double inequality sign that represents the sort of if statement for if this is bigger, choose that, or say that. Similarly, this conditional probability is probability of H0 naught times the conditional density on H0, again, over f of x. Right? And these are just our definitions you might want to review from the conditional lecture if you need to. But otherwise, we can look at this and say, oh, well, if this is the case, I can get rid of both of these and to simplify things. And I'm going to pull the two conditional probabilities over and the two priors over. And by the time that's done, I'm going to end up that I'll have the ratio of the conditional density on H1 to the conditional density on H0. And I'm comparing that to the ratio of the prior probabilities that's been flipped the other way. And I always, students sometimes find this confusing. They shouldn't be the same ratios. The idea should be when you cross multiply, things should be back with the thing they started with. So if this is H1 over H0, this will be H0 over H1. So how the two densities are related to the two prior probabilities tells me how to decide. More generally, we can think of this as a general thing. This is such a common thing that it has a name. This ratio of conditional densities is called the likelihood ratio. That's basically saying what's the likelihood of the data for each of the two hypotheses and how do they compare. And this is the ideal case if I know the priors, but we'll see that many decision rules come down to comparing the likelihood ratio to some threshold. Right? So we'll say that now this tells us our new decision rule if we sort of summarize it. Based on that, this says our decision rule g of x is equal to we'll do the other one. We'll do H1 if the likelihood ratio is greater than some threshold, say gamma. And otherwise, if the likelihood ratio is less than gamma, and again, that for the if gamma is the ratio of the prior probabilities, then this decision rule minimizes the probability of error. Okay, so again, that's a very fundamental thing. Let me just page back to it for a second. Because the likelihood ratio, in fact, this is so common, people often write this as a shorthand as capital lambda of x. And again, in the definition we have, because we use it a lot and all those extra probabilities get cumbersome, people often write this as P0 over P1. So choosing things this way will minimize things. And this sort of, to give you an intuitive model, very often what we're looking at, if I look at those things, I could sketch sort of what all this equation is saying. It's sometimes helpful to have a picture in your head. I might say, as I look at my random variable x, I might have a model that looks something like this, that this is the probability of H0 given x, and then I've got something going the other way like this, where they both are sort of ramping up to 1. This is my probability of H1 given x. And what I'm doing is, for a given value, some measurement I get, say maybe here, of this x, what I'm doing is I'm basically just comparing these two and saying, right here, this one's bigger, so for this value of x, H1 was more probable, I'm going to guess it, right? You're always going to pick the more likely thing based on that. And again, these probabilities, as we've seen, include the priors already, right? We saw that in the earlier definition. I said they're sort of like taking the prior and then renormalizing it based on the data, but they do take into account how likely each thing is. And so in a picture like this, actually, I didn't really want to scroll down, I wanted to go to the previous page. Let's go back up. In a picture like this, what we'll end up with for the decision rule is sort of a threshold here at gamma. And everything on this side of the probability will say H0. On this side, we'll say H1. We have to be careful when we look at this, and this is if the two probabilities look like this. Depending on how you define the hypotheses, H1 might be bigger on the left and the right. So don't get locked into this picture. This is just an example. And sometimes I've seen students get it wrong because they assume H1 is always bigger than X. Depending on what X is or how it goes, it might be bigger, or one might be bigger to the left or the right. Sometimes it's like an interval inside the middle, so that if X squared is less than something, you choose 1. There's a lot of different forms, I guess, without getting into it. So this is a helpful picture, but it's not the only way decision rules look. Okay, so that's a lot to digest, but that's the big overview of binary hypothesis tests and their vocabulary. The next video I'll record will be an example showing how we apply that to the communications example and get a decision rule, and we can work with that to talk about probabilities of error and things like that as well. All right, again, this is John Buck. Here's the closing credits with all the information on my university, my college, my department, how to look up information on our grad programs if you're someone from outside UMass who's interested, and the technical details. All right, thanks for your attention, and I'll look forward to seeing you next time.